Hope you had a good lunch. I was waiting because the women in ICT just finished, so I was waiting for them to come in. This is the lightning talks. As you can see on the screen, very short presentations, various topics. There's no thematic approach to this session. The speakers talk about whatever they've come up with, future technologies, or currently what they're working on. But the only thing is the time limit of each presentation. Each presentation is for 10 minutes, and we usually display the clock on the screen, but we can't make it this time, so I'm going to do it on my phone, and when the time's up, 10 minutes up, I'll say time's up. So the 10 minutes takes from where you are, where you're seated, start working from there, I'll start my clock. Okay, so I see Jody is coming up because that's his first presentation. So Jody Pallet is going to talk about, if my colleagues can scroll up, please. RSC 8273, unique prefix per host. And, okay, your time starts now.
Yeah, okay. We have something to change the slides, I guess.
Okay, I'll stop and
Don't worry, it's okay. Start now. Okay, so what is this about? Well, this is actually not a new protocol. This is using basically existing protocols that we have since we started designing IPv6. The idea is to be able to, instead of allocate a single address to an interface, to allocate a complete /64. And that provides, for example, in hotspots, a very simple way to isolate users from other users, or in data centers to allocate a complete /64 to a server, so virtual machines inside the server can have their own global IPv6 address. Okay, so use as scenarios. In fact, this is something that we have been doing in cellular. In cellular, by definition, every cellular phone in each PDP context get a /64. So basically, the concept is just the same. And then you share this /64 among other devices if you are doing tethering. The cellular phone becomes then like a kind of router in addition to a host to allow those shared prefixes among the other hosts, right? So I am going to jump straight to some of these specific examples. Hotspot. Let's suppose we have an ISP that is allocating to a hotspot provider in a specific hotspot a /48, and then this hotspot has a number of access points, and instead of just giving each access point a /64, is giving every access point a /56. And then we have one user with a laptop connecting, and instead of getting a single address, we'll get a complete /64. So if the laptop has virtual machines, he has the chance to use one individual IPv6 address for each virtual machine. And the same if other users start connecting with similar situation. You can mix and match, and you can have some users having the standard allocated single address, but you can have all of them using a /64 in each interface. Okay, so that will be a very, very simple scenario. We have another scenario, which is a data center. Let's suppose a similar case. We have a data center which is getting from an ISP a /48, and then he decides to allocate to every rack one /56. And then we have one server with a single interface, and in this interface, the physical server get a complete /64, and then there may be virtual machines or whatever needs for multiple addresses from the single /64. If you have a server that has two interfaces, you can exactly the same allocate one /64 to every interface, and so on and so on. Okay, so that will be the case for a data center. And then more interesting scenario. Let's suppose we have an enterprise network. Let me go back to show you. The go back is the red one. Yeah. Okay. Let me stress something here. In these slides up to here, I have been talking about having IPv6, and I am not saying I don't have IPv4, so you can still have the standard IPv4 mechanism for each of these interfaces, okay? But now here, I am talking about a different situation. I am still getting as an enterprise a /48 from the ISP, or it may be perfectly I am an end user provider independent from APNIC, and I am getting my own /48, never mind. And then I have different switches with layer 3 capabilities, and each of them get /56. And let's suppose, and this is the difference, now I have decided to run IPv6 only in this enterprise network, okay? So that's the difference with the previous scenarios. In this case, I am only giving a /64 and non-IPv4 addresses to those hosts in my network. So we have different kind of devices, IP phones, laptops, whatever, desktops, having individual /64s. Of course, they are isolated from the others because it's a different /64. If they need to talk among all of them, as in the previous cases, they need to go to the first hop. And what happens if there is a specific application that needs IPv4? Basically, it can run an on-demand VPN using IPv4 on top of IPv6 to get that connectivity. So the application runs, and when there is no traffic, it falls down the VPN, and that's it. So it's a more interesting scenario. We have actually tested it, so this is something that is not just an illusion, it's something that is working, and I think it will be very interesting because it gives you the point where today one of the reasons you cannot get rid of IPv4 in some enterprises is because there are all applications, and of course you still want to run those all applications, but you are trying at the same time to say management cost running IPv6 only. So this is a simple way to do that, because maybe it's just a few number of users running these IPv4 only applications, and it's easier than managing dual stack for the complete network. And that's it.
Thank you. You can take questions.
Questions? No questions?
Comments?
So more time for the next one.
So next one is issue how to create telemetry character. I didn't start the clock.
Okay. My name is Shishu Tsuchiya, Arista Networks Japan. I'd like to explain how to create a telemetry collector. To be honest, this spell was wrong. I wanted to use collector, but my story is collector, telemetry collector, but which is collection and modification telemetry data. So I think this title is much for my presentation. At first, I'd like to explain what is telemetry. Telemetry is push-type monitoring system. Every device is push every state change to the collector. And the collector gathering telemetry data from every device is then instantaneously. And some people, how to back this?
The red,
Small red one? Many people considering telemetry is next generation SNMP. So I'd like to explain what is the telemetry benefit. This guy using polling-based monitoring system, and the device is pushing to the data to the collector. The polling-based system check interface state every 1 minute, but actually switch state switch state once down and recovered within the 1 minute. In this type of event, polling-based monitoring system cannot detect this event, but stream state-based telemetry monitoring system can catch this type of events. I'd like to compare difference on telemetry and today's SNMP and syslog. Event notification, SNMP and syslog. SNMP use trap type the push type notification, and the telemetry, of course, push type the monitoring. And the state monitoring is polling based by the SNMP, but telemetry is push type monitoring. The data format is SNMP using MIB, and the syslog is a text-based information. Telemetry is defined data model, which is reusable and to be easy analyze data format. And virtualization, SNMP sometimes events showed with topology map, but telemetry is compare the streaming data. I'd like to focus this point from a next page. This is network measure map, OSS of NMSO's open sources. And this data is from, from polling-based data, like MRTG and cacti. And the good point is traffic utilization mapping to the network topology map. And this is telemetry data. Telemetry is interface counter state pushed to the corrector periodically. And if you, I'd like to add animation to the slide, but size of the presentation is limited. So I updated my animation to the YouTube. So if you'd like to check this one, you can show what is the telemetry data. And the telemetry data can compare between the interfaces, devices, and also they have time scaling. So, and the telemetry data can show some error counter, but NMS-based network weather map is instinctive, I think. So, we combined telemetry and topology map. And I also update the animation to the YouTube. Can we right? This is animation, but the animation shows create topology map from telemetry data, which is LLDP neighborship automatically, and the telemetry data mapping to the topology. And this shows the topology traffic utilization, traffic throughput, and error counters. And this also has time scaling. So this is conclusion. Telemetry data is comparable between the interface devices with time scale, but it is a little bit less instinctive. So if we consider that if telemetry data into the network topology, I think it is a more powerful monitoring tool. This is our turnkey solution product, Cloud Vision cloud vision effort, but the philosophy is would be also same and useful for the OSS and do it yourself systems. My presentation is ended. Thank you for attention.
Thank you, Sishya. Next one is Ulrich. Dr. Ulrich, simulating the behavior of satellite internet links to small islands.
All right, kia ora tātou. So this is a talk that in an extended version was actually given at APAN 2018 in Auckland recently, and I got a call or an email a day later from the program chair asking whether I or my student could attend. I couldn't. My student attended, came back with a best student paper award for it. So I thought I might share a little bit of that here. So essentially it's about the simulator for island satellite networks that we've been building. So essentially the problem we're investigating is that when we have satellite connections into Pacific Islands, then typically they will have very long latency and low bandwidth, and that leads to all sorts of wonderful problems. And there are essentially two types of potential solutions for this, short of running cable to the island. You can use this, and this is the classical solution, you can use a performance enhancing proxy. They're typically TCP connections splitting, not all of them. They can partially solve the long RTT problem, but at the price of having the connection split, which violates the end-to-end principle and can create tricky failure modes. And we're also looking at coding-based solutions where we're basically doing error correction coding across packets, across the point where the packets are getting lost, and that's at the input to the uplink satellite modem. So basically, cut a long story short, in this talk, how do we demonstrate what is happening on such a link, with or without coding, performance enhancing proxies, etc. Included. So we decided to go and actually simulate on hardware, because the moment you try and start simulating something like this in software, you end up with a problem that it's a highly computing intensive thing. So we ended up building a large simulator that I'll talk about a bit more in a moment, and we want to be able to simulate a large number of different links. We want to also simulate with realistic demand levels that we can, however, also control to a certain extent anyway. We want to have a good demand profile, so we want to have a mix of short flows and long flows. And we also want to take into account that between the satellite gateway on the world side and the servers that actually send data to the island, we have a latency distribution. So how do we implement all of this? This is our topology. It's actually a slightly out of date topology slide. We've added one or two little things, but by and large it's still all right. So essentially what we see here on the left-hand side is our island side, and our island side clients are represented by a total of 96 Raspberry Pis that act as island clients and 10 Intel NUCs. So they sit on a bunch of trays in a 19-inch 7-foot rack. And there's also a special purpose Pi on the island side. On the world side, we have a bunch of world servers. Those are the ones that actually provide the data that we're sending across our simulated satellite link. And the simulated satellite link is this thing here with the actual satellite link proper emulator sitting in the middle, flanked by coders and PEPs on either side, and a number of copper tabs that allow us to actually listen in onto the traffic that runs across. So this is what it looks like in practice, or at least what it looked like a few weeks ago. I haven't got an up-to-date picture yet. We've added a couple of big storage servers here. Of course, we were running out of storage space. So on the left-hand side here, you can see, well, my student Lei Chan, who is my co-author on this. So here you can see the trace with the Raspberry Pis, Pi power supplies, Intel NUCs up here. This is the satellite chain with the satellite emulator in the middle, the coders and everything, copper tabs down here. These are capture servers that listen to the copper tabs, and these machines here, they're essentially the servers on the world side. So We're running this with purpose-built software to basically be able to control the load level and provide the demand profile as well. We use a lot of standard tools that you probably all know, and we've written quite a bit of control and analysis software for it as well. So how do we run an experiment? So a typical experiment starts with configuring the actual satellite link, so make it a MEO or a GEO, but also configure the buffer size on the input here. Then we configure any PEP or coding solutions around it. And the next thing is to then start the capture. We first start on the island side because we want to make sure that when we're looking at things like packet loss later on, that we're capturing everything that's entered the link on the world side. So we'll start capturing on the island side of the link first. Then we capture on the world side of the link. And when we're taking this down later on, we go in the reverse order. Then once we're done with this, this wasn't meant to. Okay, so once we're done with this, what basically happens is we start up the world servers. They're now ready for operation, and we configure each of them with a different latency to the satellite chain. So we get the latency profile that we want to run. And the next thing that then happens is we start up the clients on the island side. They randomly connect to the world servers, get a random flow size value from the distribution that we've got configured there, and then basically download that amount of data through the satellite chain. So this creates the background traffic that we want. Then we officially start the experiment by having a referee type whistle packet that's being sent from this special purpose Raspberry Pi here across the satellite chain to this. That packet gets caught in all of the trace files, and so we have a common timestamp from an IP address that doesn't otherwise turn up. So this establishes a common point in time in all of the trace files. We then start a large file transfer from a special purpose server here to one of the NUCs over here. This allows us to time a specific transfer. So we can, rather than having transfers of random size, we have one of fixed size here that we can monitor. And the other thing that we're doing now, no longer from this server, but from an additional one that we specially commissioned for this, we're also running a rapid fire ping, and the rapid fire ping basically produces a round trip time log, and that round trip time log essentially tells us how full the queue at the input to the bottleneck is. And so this tells us whether our TCP queue or queue basically of IP packets here oscillates with the TCP windows opening and closing on the world servers. So once we're done with this, we basically break everything down, pull all the logs back and the traces. So we do quite a bit of quality assurance initially before the experiment. So make sure that the system works properly. Then post-experiment check, we make sure that all of the machines actually turn up in the logs, that the start and stop signals are present and everything, and that all nodes participated, and quite a bit more. I haven't got much time to talk about now. So this is what, for example, the queue sojourn time for a classically a dimensioned queue on a 16 megabit per second geolink under relatively light load looks like. So we see that this is the time when our large file transfer is still going here. We see we're getting queue sojourn time going up to 200 milliseconds here. So this is a standing queue forming. Once that's over, we're having light load, and there's virtually nothing in the queue. So if we repeat the whole thing with higher load, what happens is we're getting standing queues all over the place, and this is something you can see on live satellite links, quite extensively. It's one of the reasons why we're now recommending that if you're dimensioning buffers for satellite links, that you're dimensioning something that either is something like CODL with a very very small standing queue allowed, or alternatively that you're putting a much smaller buffer in. And we've just had a paper accepted into IEEE GlobeCom in Abu Dhabi later in the year that drives that point home. So if we're bringing the Q down, then what basically happens is that we now get a Q that actually oscillates nicely within the buffer. So this is, it's actually you know, acting as the shock absorber. It should be taking, it's not having any standing Qs. So this is a sort of more summary result. So here we're looking at comparing geostationary with medium Earth orbit links. So what you can see here is basically the blue one being the geostationary and the medium, and the red one being the medium Earth orbit links. So interesting thing that we can observe here is that for the medium Earth orbit links, the individual file transfers achieve a much higher rate up to a certain load point.
Sorry, Ulrich, time's up.
Time's up. Okay, fine.
Thank you.
Thank you.
The next speaker is Shishio again, Genog Hackathon.
Shishio Tsuchi again. I'd like to explain the Genog Hackathon. I want to do this presentation as a Genog 42 program committee member. This sticker is Genog's Hackathon's sticker. Next. I'd like to quickly explain what is Genog. Genog is Genog Network Operators Group, and membership is mailing list subscribers, which will be over the 6,000, and meeting basically twice per year. Genog 42 held at Tsu City, Mie Prefecture, hosted by the ZTV, who is a local internet service CATV provider. And the meeting, the total attendee over the 1,000 and the streaming over the 600. How to organize the Genog meeting? ZTV is this time the hosted, and host company gathering sponsorship and provide venue and organize the social event. And Genog is call for staff every meeting, and Genog 42 execution member attend as a volunteer, and they organize the meeting and the program selection. And all of the Genog members over the 6,000 and can try the CFP and to speak some program on the event. And also they can try to the staff, and also they can attend to the meeting. The Genog Hackathon was one of a program. And who organized the Genog Hackathon? Taiji Tsuchiya is one of the leader of the Genog Hackathon this time, and he worked at Itochu Telecom Techno Solutions. And several members joined Genog Hackathon staff, NTT, KDDI, also some Web 2.0 company, Duang, Mixi, AWS, and also Kumamoto-san is from Mitene Internet. Mitene Internet is a local internet service provider. He also contribute, make sticker. And I also attend as a Genog program committee member, and I also provide some cloud environment which has one Ubuntu and 5 virtual EOS router on the cloud. The big theme of the Genog 42 hackathon for improvement of the daily network operation. This is a picture of the Genog 42 hackathon and scheduling. Genog hackathon start at 2:30 and introduction theme at which want to the developed and group discussion and developed by themselves, and they at 7 p.m. presentation and demonstration as a result. The number of attendees was 30 and staff is 8, so over 40 people gathering in same room in whole day. This is theme of the January 40th, all of theme of January 42 hackathon, like this PGP peering, manual creation, configuration automation, and chat ops, telemetry, and network operation automation. I'd like to some example of the January hackathon. One, this is a web portal. The operator put on some BGP parameter, then the Python script create Ansible playbook. Ansible playbook configure the BGP automatically. And this is a Google form. Some operator called Google form. Then the API create BGP rule on the BGP root reflector. Then the BGP root reflector send to the filtering rule to the BGP client, RR client. This is Slack. Some operator call chat to the Slack, chat to the bot on the Slack. Then the Slack create configuration from the template, and at the same time, the Slack pull request to the GitHub. GitHub checks some configuration, and also the, GitHub create configuration by the napalm. The napalm create configuration on the devices. This is a sample of the this event. What is next? January 43 will held 25 of July at Yamanashi Prefecture. And the January hackathon planning will be held 22nd July. If you interested in January and January hackathon, please come to the Japan. My presentation is ended. Thank you for your attention.
Thank you, Sisho. I got one question. We, APNIC, we also organized a hackathon in the last conference in Kathmandu. We did it over 2.5 days. I was just trying to understand, how you managed to do it in a half a day. You started at 2:30 and you finished around 7:30. Did you provide information to the participants beforehand?
They discussion on the Slack and mailing list about the theme. And also some team is preparing 2 weeks or something.
So there was a preparation before the hackathon happened. All right. Okay. Thank you.
Yeah.
Next speaker is the Masataka for PMDB front-end translation project.
Good afternoon. I'm Masataka Matari from JPIX. I'd like to talk about PMDB. As you can see this top slide, PMDB has a project trying to internationalize PMDB web page. It's called the PMDB front-end translation project. It's PMDB web page, as you all know. And let me introduce briefly about PMDB. PMDB is a database about interconnection. It contains network providers and data centers and IXs for network operators. They are working with PMDB for PM coordination and network operation, as you all know. And this slide is why do IXPs recommend PMDB to members and why it's important in PMDB web pages. PMDB is a kind of profile card as a network provider. We can look for peering partner each other with peering DB. And peering partners in a peering event. But unfortunately, here is no peering partners in APNIC meeting. But I think in Apricot meeting has peering partners in peering session slot. And in their peering partners requires network providers to show the page for self-introduction. And 2 point is content provider has a requirement for peering. And content providers, as you can see this slide, Apple, Cloudflare, Dropbox, Facebook, Google, Limelight, Microsoft, they require peering DB registration for introduction of peering for peering of network providers. All of them say you must have a peering DB entry. So finally, peering DB become more important for network providers for peering with content providers. And the peering DB is a useful database, but it's user thing in Japan. Japanese network providers of Japanese language. It's a kind of language barrier, as you know. And so every Japanese IXP provider provide procedure in Japanese how to register on peering DB to our IX members. But once they have registered, they use peering DB without any problems. And Japanese IXPs, including JPIX-me, want to make it easier to register for Japanese network operators. But it's not reasonable. Japanese IXPs have to prepare a common procedure in Japanese. So I looked for more better solution or approach. So peering DB team has started this project. I think it's great approach, and I fully agreed with this project. Internationalization in peering DB. And if you're interested in this activity, please join this activity. If you have interest to internationalize peering DB, please post a new request. Please generate a local file on issue page in GitHub of peering DB. And peering DB generate a local file for translating to their languages. And you can edit local file in your language on local file generated by peering DB team. And once you have completed editing the files, please do pull request in GitHub. And then peering DB team uploads the local files on the beta website. So you can do checking if your translation is good or not on beta website. before the publishing on official website. And at last, PMDB team will upload the internationalized page on official website. And this is current status on this activity. Some languages is underway on this project, as you can see this slide. In ethnic region, Indonesian and Telugu language in India, simple Chinese and Japanese is going translation activity. Not your language in this slide. Please join activities. I think not many economies in ethnic region on these activities. And this slide is PMDB page in Japanese. As you can see, this PMDB page has Japanese languages. And this is conclusion slide. If network providers is your economy have language barrier in your economy, PMDB internalization might help them, their network providers. And the PMDB internationalization project is underway by using GitHub. And IXPs should provide a good, better environment to piracy in your economy. Thank you for your attention.
Thank you, Masataka. Thank you very much. The next presenter is Martin, FR routing overview and current status.
Okay. For the ones who see me as Hungry Electric, this is a TEPA project, so here I'm talking about as NetDev open source routing. So I'm not sure how many here actually know what FR routing is, also sometimes heard as free range routing. It's basically a routing stack, so it's not a full router, it's a routing stack, so it's just a routing protocols. You still need a forwarding plane. You can use a Linux box or any Unix box stuff. It could be a virtual box. You can actually get white box hardware and have like hardware forwarding to with like many manufacturers there. It implements basically about all the common routing protocols. So RIP, RIP-NG, OSPF and all that stuff. We also have more exotic things like Babel. We have now EIGRP in the first version, maybe not that perfect yet, but happy to hear about bugs or something in there. It is a fork of Quagga. I hope a few of you heard about Quagga. We started forking that early last year, about April last year. And yeah, it's used by a lot of virtual routers these days already. There is quite a big uptake. White box vendors are using it, network providers with like doing full stack routing on it too with it. So who's behind the fork? These are like some of the companies currently who officially admit on supporting it. There are a lot more companies who are using it, planning to use it, who are not yet willing to mention it publicly. It basically, one of the first start you may know is Cumulus Networks, who basically is very active on there too, who basically started that stuff with us. The key differentiation to Quagga or many other routing protocols, we tried to, before the progress we felt was like way too slow, we wanted to change it. So everything is basically GitHub based. We do with pull request. All the submissions automatically tested there, do a test system there. We have like frequent, like weekly calls from all the people who are interested to talk about open issues and pull requests. There we have an elected maintainer and elected steering committee. And the common assets are like held by the Linux Foundation. So we tried to make make it up a lot more in automated things, so we have like fast progress and don't have to like slow down too much. And so it's quite a fast progress, as you can basically see here. So what kind of happened? We were like surprised, I was very surprised how fast it took up. If you look on the top, the gray section, that's basically about how many commits were in Quagga from 2002 basically, when they started with on Git until we started the fork. We did, at that time, it was Quagga by 1.1. We added a lot of enhancements in there for coming out with a version 2. That was basically, we went from like about 4,000 commits to more than about 6,600 commits. And then since that version came out, you see that we are now here near to 13,000 commits in Git already. You can see also from the bottom line there, below the arrow, we progressed in this about 1.5 years, more than 2,000 pull requests. So that's on average about 4 pull requests per day. We also have very fast progress in versions. We came out first with version 2.0 because we wanted to show a separation over the 1.1, because we had a lot of features there. October last year 3.0, April 4.0, July 5.0, and we're now trying to go in a 4-month cycle, so beginning of October the 6.0 version is supposed to come out. It's currently in beta testing. So from looking at the features, what's got added, so this is all on top of Quagga, which you may know already. So we added unnumbered like support for most protocols. We added LDP for like if you run Linux or OpenBSD where you have an MPLS stack, you can do with LDP, you can do MPLS router. We had VRF Lite, the JSON support, quite important for the output, so it's easier to parse it. We added then BGP eVPNs, PIM sparse mode, PIM, the sparse dense mode is there too, part of it. Then next hop routing protocol, I don't really know anyone using it, but I'm sure there's an interest. We added RPKI basically this March in there. We had more eVPN stuff. Babel got added, ERGRP as I mentioned before. So Babel, if you're not familiar, it's quite a bit in the wireless world sometimes used. We have segment routing on OSPF v2, we got that in there too. We have now, with the version 5, we have as an example a policy-based routing. So if you're familiar with some routing platforms where you can do policy-based, also based on routing source, destination, and maybe even port number, do some routing there. So you can do weird rules there. We have the VPN VRF route leaking. We now have the next version coming up is BFD, the bidirectional thermal daemon. We have also source test routing for ISIS, which is coming out in October. After that, unfortunately, making 6.0, which I kind of like, is the Open Fabric protocol, which will be coming out in the next version after 16. The ones you want to try it out, on GitHub, there is like, you find releases, you can download packages for a lot of the platforms, or you can go ahead, compile it yourself. FreeBSD, it's in the official ports. And some of the other OSs, you find build instructions how to do it. And yes, we are basically obviously very interested for anyone to join the community. Try it out yourself. If you want to build a cheap router, just like 10, 20 gig of bandwidth needed, then you can use that, load a simple Linux on it, and you have your free router. Very simple to do it. No need to call up any big vendor, tell them lots of money, you can fix yourself. Open community, just let us know if you have problems. Yeah. Okay.
Thank you, Martin. Questions? Oh, yeah, you can take questions. You got 3 minutes.
Cool.
Or comments? Any questions or comments?
Curious, anyone here who knows FR routing already? Nobody. Wow. Okay. I hope in a year or so everyone would put their hands up and say, yeah, tried it. So yes, I say like we love, especially from the community there. So there's like we are worldwide like based around it and have development. So if people want to join and a fun project, cool engineering, go ahead, join us.
Thank you, Martin. Next speaker is Guy Roosevelt, how to monetize IP reputation. Guess the speaker is not in the room. No? I know they're outside, they have a desk outside. But otherwise, we have the Jodis ready. So for those who just walked in, yeah, if you could, someone check, please. Thank you. For those who walked in later, after the session started, this is a lightning talks, and every speaker gets 10 minutes maximum. So that's why we have to cut off some speakers if they're going over the time. But we still have time. So if you have anything to discuss or anything you want to come up here and talk about it, no need to have slides. You can just do it from your notes. Just be ready. Let me know. Once we finish, Jody just submitted another one. So once we finish Jody, we probably will still have time for something else. I think Guy just walked in. So can we have his one NS focus, please? You have 10 minutes. That's the phone button.
Ah, great, thank you. Hi. Good, great. Okay. My name is Guy Roosevelt. I am the Director of Product Management for Web Security and Threat Intelligence for NS Focus.
Sorry, we were waiting too long for you.
They told me 3:15. I was about to walk in to see the guy before me. So, no worries. So what I'm here to talk to you about today is how you can monetize a certain type of threat intelligence that would be interesting from a tier 1 service or tier 2 service provider perspective, but be very, very important to give to your enterprise type customers.
It's coming.
Okay.
That's a technology.
That's okay. Again, there we go. Okay, great. So, how to monetize IP reputation. How many people here know what IP reputation is? Anybody? Okay. So, what IP reputation does, any IP address that does something malicious on the internet gains reputation or notoriety based upon the type of bad things that it does, how often it does those things, and when it stops doing those things. So what you do is we have the ability to track IP addresses worldwide that do attacks, become part of botnets, become spammers, all sorts of stuff. And we can track them as individual IP addresses or as groups within ASNs. And this is very important from a provider perspective because you guys are selling usually large IP pools to enterprise customers. So the idea is if I can track these things by these 10 different categories, your enterprise customers like to know if they're doing bad things on the internet. Are they attacking other places? Because if they attack somebody else and it's traced back to them, there's a liability issue, right? They can be sued for launching an attack against a nation state or something else that happened along the way. The interesting thing about IP reputation is an IP address can have more than one category. So it could be a spammer and a phishing device, or a botnet and a web scanner, or something else along the way. So there's no single category. An IP address can do many bad things depending on the kind of malware it's infected by. Pushing the button. Okay, just to give you an idea, on average, this is the top 20 list for the world who have the worst IP reputation. And the way we do this is we look at the number of IP addresses that a country owns in their space, or for all ASNs. We look at the number of IP addresses that have been infected doing something bad, and then we do a percentage calculation. The reason why we do this is because what's interesting is not the absolute number of IP addresses do something bad. If you look at the absolute number of IP addresses, by definition, China and the United States will always be the worst people, right? But as a percentage of all the users in the country, knowing what the percentage is gives you a better idea of how bad the reputation is in terms of how secure the country is. And for the last year and a half running, Vietnam has been #1 in terms of worst reputation, which means they have the most affected devices per capita in the world. Iraq, Merida, Pakistan, these things all tend to be about the same, but consistently Vietnam has been #1. And then what we do is we look at the country, and then we say, well, based upon that country, how do we look at the division of IP reputation for each of those IP addresses? You can see here there is 36,000 spammers, which is over half of the spammers in Vietnam. Or the IP addresses in Vietnam as being bad, for example, versus if you look at the actual number of devices that are spreading malware in Vietnam and other places, it's very, very small. So you can see that the type of things that's easy to do in Vietnam is their infected systems are going out and spending out lots of spam email. If you look at Japan, we took at the top 20 most infected ASNs in Japan just for fun. And if you look at the distribution you see here, you see the very long blue bars. When you look at the blue bars, that means that most of these IP addresses that are infected are botnets of some kind or another. And what's interesting here is very consistent that the majority of IP addresses that you see are some kind of botnet, and then there's a couple places where it's not botnet so much as they too are mostly spammers. So trying to understand why the entire ASN is mostly botnet and another ASN is mostly spammer, that's very interesting because it talks about the spread and infection of bad things, but that's not important for this particular conversation. What matters is understanding that you have an ASN, you have an enterprise who is subscribed to your ASN, have a block of IP addresses, and some number of those IP addresses are doing something bad. That's what's important. Just for giggles, this morning when I had a moment, I actually went and searched to see what Fiji was doing because I had a lot of people from Fiji come talk to me today. And I don't have the absolute number of IP addresses that Fiji has, but what's interesting to see for Fiji is there's a total of 66 IP addresses that have done something bad in Fiji, and most of them are spammers too, as you can see. Spammers, scanners, and botnets. So that's a very interesting distribution that you see here in Fiji. All right, just to give you an idea more about reputation, there are some ASNs worldwide that are completely 100% DDoS. That's all they do. Okay, that's actually pretty bad. And then here is actually an example of ASNs around the world that are completely 100% infected. Every IP address in their space is infected, just to give you an idea. So these are the kinds you deal with. And again, we see a lot of these infections in Asia Pacific because Asia Pacific has a large number of systems that are unpatched, unprotected, and don't have as good endpoint security measures associated with them. All right, this is just to show you why this is important, because this is that you can sell this to your customer is, this happened last year. This is actually a small island. Sao Tome and Principe is a small island off the coast of West Africa. It's one of the smallest nations in the world. And if you look at them, 75% of the organization of the country is attached to cell phones. 25% has access to internet on landlines. But what's important here is before July of last year, they were almost nothing on my IP reputation list. They had like 2 IP addresses that were infected. And then overnight in July, they had over 1,000 IP addresses that just showed up and being infected on all their phones, which is a very large percentage. So they went from being no place on my list to number 7 in the world in a very short period of time, because pretty much everybody in the country who have Android phones downloaded a Google app that week that was infected by the WireX virus. WireX was in over 300 applications on Google Play Store at the time before they discovered it, and infected probably 40 million phones worldwide within 14 days. It's terrible. But to see a microcosm like this, where you can see 2 ASNs, a very small ASN that handles everybody at home, and a very large ASN that handles all their cell providers, and all of a sudden those cell the cell phones got infected overnight in a large percentage, gives you an idea of the kind of things that happens worldwide, including things we see like this here in Asia Pacific. That's why Vietnam is such a high rate. So, having seen all this stuff, and this is just the small ASN, you can see in April and in July had almost no change in the number of infected systems, so everything was all on the mobile phone end. I'm not going to go through all that stuff, but skip. So how do you make money in all this stuff? So the idea is you can provide your customers an IP reputation monitoring service that says, hey, we'll go ahead and monitor all your IP addresses because you guys can see all this traffic in real time, and then map them to a threat intel database, an IP reputation list that says, in the event that my update shows on my IP reputation list, your IP address now shows up on my list, we'll tell you and tell you what it did in terms of the credit level and in terms of the type of attack it did, and inform you why this has happened. This is actually very important. NS Focus, we do a lot of this for a lot of telcos In Japan, we work for a telco. We monitor over 100 million IP addresses in real time. And we, on average, on a daily basis, get anywhere from about 20 to 300 IP addresses every day of one of their IPs shows up on a reputation list. We have to tell them so they can go remediate this. This is actually a very lucrative service because you can sell by the number of IP addresses that you monitor. You can automate this process, and it's relatively cheap to do. Once you have a threat intel database that you can map to, you guys have all the IP addresses that you can track. Oops, it's relatively getting a database and a script that just basically marries the two together every day to see if anything on your ASNs show up on the database list. And boom, you send out an email that looks like, oops, I thought there was an email in here. An email that says, hey, these are the IP addresses that showed up and why. Okay, and you can charge a lot of money. You can charge anywhere from a few dollars per IP address, depending if it's a small number of ASNs to a large scale for enterprises. We're talking tens of thousands of IP addresses.
Sorry, Guy, your time's up.
Okay, thank you.
It's
You
10
can
minutes maximum.
Yeah, sorry, 10 cents. There we go, thank you.
Thank you.
Sorry.
We can still take a few more talks, but I really request that it should be on technology, not sales or marketing. So if you have any topics that you'd like to discuss, no need to have slides. But if you do have slides, just give it to my colleague on the desk. They can quickly put it on the screen if you have on the USB. But otherwise, we are still open for a few more talks if you have anything to discuss. Jody, here's next.
So actually I didn't have this talk prepared, but I saw that there are 30 minutes left in the agenda, so why not? Okay, so Happy Eyeballs version 2. What is Happy Eyeballs? Happy Eyeballs is a way, okay, let's say in another way. If you have a dual stack machine, the thing is that we want to prioritize IPv6 traffic to help the transition. So if we have the balance today of IPv4 traffic, and this is the IPv6 traffic, as much as we give priority to IPv6, we change that balance, okay? More servers or more contents or more applications have IPv6 and the clients have that as well. If we give priority to IPv6, the balance will change like that, okay? So what's the problem with that? The problem is that the definition of this dual stack transition technology didn't tell how much time an application like a web browser should wait before falling back to IPv4. So some operating systems at the beginning were doing 21 seconds wait, okay? And obviously that's bad because if you are in a browser, it means the web page times out, okay? So that was sorted out a few years ago, actually in 2012, which this mechanism that we call Happy Eyeballs version 1, RFC 6555. And what that mechanism is doing basically is starting synchronously a query for the quad A record and the A record, and then waiting for the response of bot, and then starting the TCP, okay? Now, what that means in reality is that if you get the response for the quad A record before the A record, you are wasting all that time, okay? I think it's easy to understand that in the slide. So what Happy Eyeballs version 2 is doing? Apple has been using us as, you say, guinea pigs during a couple of years before publishing this draft, and we had a new version of Happy Eyeballs implemented in iPhones, and this version was trying to look for ways to improve this mechanism. And at the end, they submitted, after 2 years of testing, they submitted the proposal to B6 Ops, and we have this situation. Instead of synchronously, we start bot the quad A record query and the A record query, but whichever comes before keeps going, okay? So we changed the mechanism to wait for bot to which one comes earlier, and we are done. So we are saving a lot of time. Basically, what this mechanism is doing is updating the default address selection mechanism that we have in IPv6, So instead of keeping the mechanism, depending on the responses that it's getting, typically waiting maximum 50, 100, 150 milliseconds instead of the 21 seconds that was originally done by some operating systems, we changed the priority of the different addresses, both B4 and B6. Now, is that good? Is that bad? It's good for the users. Actually, Happy Evolves gives the users a better response for any service. The thing is that for ISPs, this is bad, because if you have a problem in your IPv6 network, because Happy Evolves, you will not get complaints from your users, so you will, well, the problem will be hiding from you, unless you have a good monitoring of your network, which you should have. But I have seen many networks deploying IPv6 that have good monitoring for IPv4 and no monitoring at all, or bad monitoring for IPv6. So my proposal, and this is work in progress, is let's take the advantage that we have this Happy Evolves mechanism to also allow, well, there are other causes of problems in IPv6 networks, but let's skip that for this presentation. So my proposal, and again, this is work in progress in ITF, is let's take the opportunity for the clients that fall back thanks to Happy Evolves to report that fallback to the ISP. So the ISP has alerts in his network, hey, our clients are falling back. There is some problem in our IPv6 connectivity. That's my idea, and again, this is work in progress, nothing done yet, but stay tuned. And that's it, thank you. Very short.
Thank you, Jody. Do you have any more to talk?
I can have one.
No. Let's give opportunity to someone else. Anyone else have anything to say or anything to discuss? If not, we have to close the session early, or you may join the other one in the other room. I'll leave it open for a few minutes if anyone have any interesting topic to discuss or anything else that you want to. If not, I think I'll close this session, and you may chill out outside or go join the other session. It's still going on. And we meet in this room again after the afternoon tea break for the next session. Thank you so much.